All right, hey everybody. So today we are on topic 37, which is on time series data, which is different from tomorrow's study group, which is time series model, time series modeling or models. I forget which one. The main difference is that in today's session, we'll talk about kind of like the EDA processes or what kind of data is appropriate for time series modeling. And then tomorrow we'll talk more about the models themselves, because a lot of data preparation does have to go into the process. Well, you have to do a lot of EDA and data preparation before you can even get to the modeling bit. So the modeling bit, I think today what will happen is in a lot of the things that we cover, I'll kind of allude to how this affects your model, but we won't get into exactly how until tomorrow. So don't mind all the loose ends. I think it's great that these are just like a day apart so that all of those questions will be answered hopefully tomorrow. For the time series project, I'll let you all know that the time series project is a tough one. But very, very worthwhile. Also, you have the option to choose your own data set, which I'll explain at the end of tomorrow, or actually at the start or end of tomorrow. I'll talk about it tomorrow, what kind of data would be appropriate if you do want to do a time series project, but not use the provided data set. So the provided data set is a bunch of zip code median housing price data. So you'll pretty much have, I think it's close to 200 different zip codes and all of their median housing prices going like, I think 10, 20 years back or something like that. And the idea is to build time series models for a bunch of zip codes and make recommendations on what zip codes people should invest in. So very likely your process will be build a bunch of models, see the results of your models, use your models to forecast and see, all right, what zip codes will give you best return on investment. So that's what the project looks like. Given that context, what that means is you're going to be building a lot of time series models for that project. I'm saying it's completely okay if you want to simplify it a little bit and focus more on a single time series forecast. So for example, if you just wanted to forecast the price of a single zip code or something like stock price, you can do that as well. And I think it'll be a little bit more clear tomorrow what is appropriate for time series modeling. So those are my thoughts on the project and the data set. All right, so to get started, again, today we're just talking about time series data, time series EDA, because time series EDA is actually a pretty important component. So yeah, we'll get into that. So first, what is time series data? Time series data is specifically data that has been obtained at successive times, often with equal intervals between them. So examples, let's say you have the temperature of July recorded daily. That will give you a time series of, is it 31 days? So that's 31-day time series. Also, the weekly average price of a stock in the past year. That would be 52 data points of weekly data points. Also, you could have the average annual government budget in the past 30 years. This means you have 30 data points and you have one government budget number for each of the 30 years. So important to note is that this data just has a single number per each interval. Of course, you can do things, let's say you're missing like a few weeks of data. Let's say like the week of Christmas, you don't have stock price or something like that. There are ways that you can impute those to make it appropriate for time series modeling. But for the most part, this is what your time series data looks like. We have seen data in the past that has time components that might not be time series data. So for example, if y'all remember that movies data set that we talked about, we had month of release and year of release. Now we could use, for example, build a model to forecast overall monthly ROI for movies as a whole. And that is appropriate for time series. But if we're keeping each of our rows as singular movies, that does not work for time series analysis because for each month we have multiple numbers, if that makes sense. So because for that situation, we have multiple data points per month per year. Here we only want one. And also a big distinction between time series forecasting and regression. Both are predicting continuous variables. However, for time series, it's forecasting. So there is a distinction that we're going to make here between forecasting and prediction. Of course, forecasting is a subset of prediction, but in things like regression, time is not really an element when we're doing regression. When we're doing our housing prices for phase 2, and we were trying to figure out the price of the house, perhaps year built was something, but we're not trying to predict the prices of houses 1 month from the end of the data set or 2 months from the end of the data set. In forecasting, that's exactly what we're trying to do. We're trying to see, all right, our training data stops here. Let's forecast only in the future. So there is a distinction between prediction and forecasting here. Cool. So we're going to focus on univariate time series, which records a single observation or variable at different but equal time intervals. So here, a lot of our basic time series data is just going to be one column of values. Of course, there are ways to incorporate other data into our time series problem. We'll talk about that tomorrow. But for now, the data that we're going to see today is really just one column of data. So, and again, quick note, same thing as I was saying before, regression versus forecasting. Oftentimes data for regression and time series forecasting can look very, very similar because both are continuous variables that we're trying to predict. It can be very dependent on your business case because you could potentially do both on one kind of data, but your prediction versus forecast can yield very, very different results. And we'll get into more of those distinctions between regression models and forecasting models tomorrow as well. Okay. So now that we know a little bit about time series data, what are some characteristics? The main two things that we want to look at with regards to time series data are trends and seasonality, and both kind of give you a sense of the patterns that emerge in your data. So first, trend, overall movement of your data. Is there an upward trend? So in this example of the ETF of S&P over the past 5 years, there's kind of like an overall upward trend, and that is something that you want to note. If you're doing any sort of EDA in your time series, trend and seasonality are the first things that you should really look at. So in this case, if I have this and I'm just plotting this line graph of my time series data, I would make some notes saying, all right, there's some overall upward trend, maybe some shocks. And you would talk about, all right, there's some shocks over here. This is missing an x-axis, but you would make those kind of remarks on your time series data. So that's trend, just overall movement of your data. Seasonality as well. So seasonality is patterns that occur as a function for specific seasons, function of specific seasons. So for example, if I were to look at maybe amount spent on traveling as a time series, you might see this peak during like the holiday seasons, like Thanksgiving, Christmas, and then kind of hit a slump in like the non-peak seasons like April. And this might be something that is consistent. So that is a seasonality that you want to take note of. And depending on the frequency of your data, so let's say I have monthly data, you can say, all right, it seems like my period for seasonality is 12 because 12 months in a year, I'm seeing, troughs in April, peaks in like November, December. And that's something that repeats over the course of your time series. You can also combine trend and seasonality. So let's say you have this repeating pattern of, the peaking during holiday seasons and dipping during off-peak seasons. You might see something that looks like, I'm drawing a wavy line. You might see something that looks like this, and that is a combination of there being an upward trend and a yearly seasonality. Any questions about these two things? All right, so there's something that I actually more recently found out that is not in this notebook yet, but there's something known as seasonal decomposition, and it exists within stats models, and it's really cool. I'm actually going to look it up right now. Seasonal decomposition. And this is something that comes out of the, I want to say the stats models library. Let me look at it real quick. Stats models. Is it stats models? Let me look real quick. I think it's stats models. Does it not show the import statement? Anyways, there we go. It is from stats models, seasonal decompose. So seasonal decomposition is a really, really neat tool, and it's really good for doing like really immediate EDA, because what it does is it will take your time series and it'll decompose it into a trend component and a seasonality component, which is really, really neat. So take this as an example. The original time series looks like this, and this is actually very similar to the example I just gave. This is airline passengers, so I guess a proxy for travel as well. So this is a plot of airline passengers data set. What you can do is pass the data into seasonal decompose. Let me zoom in a little bit over here. So I'm reading in the CSV, passing it into seasonal decompose. I'll talk about what this multiplicative thing is in a bit, and then we can just plot this out. These four will plot automatically. And what's really cool about this is the original trend. This is the original data. And it breaks it up into a trend component. As you can see, there's an overall upward trend. There's a seasonal component within this trend, how much seasonality is there. And this is basically that consistent yearly pattern that arises in the time series independent of this trend. And this is also a residual. These are basically parts of the time series that are unaccounted for. And these numbers over here correspond to exact magnitude. So you can see that the trend here starts at like around 100, goes up to about 500. That's kind of what you see if we were to just draw a straight up trend throughout here. And this is the seasonality component. And this also, I have to go into multiplicative versus additive. But if it says multiplicative over here, and you can actually try both. If it's multiplicative, that means that you would just take this trend, multiply by 0.9 at these points, by 0.2 at these points, 0.8 at these points, just stack this multiplicative, multiply these lines together basically, and you get your observed trend. And this is just a residual. So residual, because it's also multiplicative, anything along the line of 1, that means it's just as is. So along the line of 1 is as is at these points over here. So for example, down here where it goes down is just sort of like an unexplained downward shock in the data. Any questions about this? Cool. I'm gonna throw this into your Slack channel later because I know it's not in the notebook. All right, cool. Let me clear this line. So trends, seasonality, things to look out for. You can do it either by just looking at it or just eyeballing it on a line graph like this. Or if you want to do it a little bit more mathematically, you can use a seasonal decompose. You can either try doing it via multiplicative, or if you change the argument to additive, because sometimes it might be additive, where instead of multiplying the lines together, you want to just add the lines together, you can do that as well. And just see which one gives you more pronounced seasons or trends. Okay, so trend and seasonality. Next, there is the concept of stationarity, which is an assumption that lays the foundations for time series forecasting and modeling. So first, let's talk about what stationarity is, and we'll talk about why we care about stationarity. So stationary data is data in which the summary statistics are not a function of time. So that means the mean doesn't change over time, the variance doesn't change over time, neither does covariance change over time. I'll tell you now that most data out there is not perfectly stationary. So you usually have to do something about it to make it stationary. And why that is, I'll get into that in a bit. But examples of stationary and non-stationary data. So something like this, that the trend is fairly flat. This is stationary, this is not, because here we see an upward trend, which yes, we can take note of that in our EDA, but for our model, we actually don't want to see this upward trend. So we'll talk about how to get rid of that or how to deal with this later. Next, variance. So here you can see, all right, there's some seasonality and the variation in the seasons is pretty consistent over time. Not like this. So maybe over here, there's more volatility or there are just bigger peaks and lower troughs over here in this part of the time series compared to like the start and the end. This is stationary, this is not stationary. Next, constant covariance. So covariance is sort of like the periods of stationarity is one way to think about it. So here you can see that maybe every period is a year. So every year you go up and then go down. But here it seems like over here you go up and down 3 times within a year. And so that is also not stationary. So ideally, we want our data to look as much as like this as possible. And we want to remove all of these noisy components of our data. And the reason for that is the class of time series models that we're going to be dealing with for tomorrow, they're actually all linear models. And just like how for linear regression, we had our four assumptions for our data, like has to be linearly related to your target, no multicollinearity, homoscedasticity, what's the other one? I forget, but very similar to that. this stationary data is an assumption of your time series models. So for these time series models to be applied consistently and properly, your data has to achieve stationarity first. And we'll talk about how to do that a little bit today, but we'll finish up tomorrow. Any questions on this idea of stationarity? Okay, so just remember to use time series models that we're going to use tomorrow. You want to achieve stationary data, so you should keep in mind like what are the things that you're doing to make your data stationary. And there are many different things that you can do for stationary. So we're going to use some examples. Okay, so stationary is important because without it, a model describing data will vary in accuracy at different time points. We sort of saw that looking at the assumptions for linear regression. If you don't have homoscedasticity, for example, you have a lot of variation in your error. Like for example, in your housing prices, a lot of people saw that you're really good at predicting lower or middle range housing prices, but really bad at predicting the luxury houses. That's just a sign of inconsistency in your model. And non-stationary data can lead to inconsistencies in your forecasts as well. So stationarity lays the foundations of these time series models. So we're actually going to talk about these tomorrow. AR, MA, ARMA models, these are all time series models. So a violation of stationarity is going to cause problems in predictions. And that's actually something that we will see tomorrow. Okay, so how do we check for stationarity? As I mentioned, a lot of data isn't stationary on its own. There are a couple ways that you can do stationarity testing. I would say the most scientific way of going about it is there is a statistical test for stationarity, which is nice. And that is called the Dickey-Fuller test. And we'll talk about that in a bit, but first let's talk about some simpler methods of doing that. So this is a data set that we're going to use. Very, very simple data set. It's just 3 years of shampoo sales data. You can see they're not so sure whether there is seasonality yet because it is, I want to say, yeah, it is monthly data. It doesn't seem to be any clear yearly trends. However, there seems to be an upward trend. And so that upward trend does violate stationarity. So how do we examine these summary statistics? One way to do it, which is not the way that you are going to do it, by the way, is just by splitting this in half. So this is a really, really quick chunk of code that takes this time series, splits it into half one and half two. And we're just going to compare their summary statistics. We don't even have to look at their covariance, but we can just look at their mean and variance first. The means are already wildly different. The first half of the time series has a mean of 203. Second half has a mean of 421. And this is obvious because we have this upward consistent upward trend that is present in this data. Also looking at the variance, it is very different. Also because there are at different magnitudes. The variance at the start is about 3,300 or 3,400, and the variance towards the end goes up to 17,000. Of course, variance is a squared number, but even so, the numbers are quite different. Actually, even if I were to square root each of these, let's see, yeah, the variance goes up from 58 to 130, or the standard deviation goes up from 58 to 130 in those two parts of the data. And this is a very, very simplistic way of looking for stationarity. Again, not the way that you are going to do this. The way that you're going to do this is by conducting the Dickey-Fuller test. So the Dickey-Fuller test is a test for testing stationarity. The null hypothesis is that the time series is not stationary. So if the test statistic is less than the critical value, or if the p-value is greater than 0.05, if the test statistic is less than critical value, we reject the null hypothesis and say that the series is stationary, and that is if the p-value is less than 0.05. I mix up my statistics, but basically you want low p-values. Dickey-Fuller test is also within stats models, and you import it over here, and you just pass it through the AD-Fuller method. So what do you get from here? Let me run this real quick. Dickey-Fuller, which is over here by itself, gives you a tuple of a bunch of values. So first you have the test statistic, p-value, number of lags used. We'll talk about lags later. Number of observations used, and then these are your critical values of your test statistic. What these correspond to and how I know this is this comes from the documentation. So these are the main things that we really need to look at. Actually, the main thing that we really need to look at is the p-value. And this p-value is a perfect 1. And the null hypothesis is that the time series is not stationary. So with a p-value of 1, we cannot reject the null hypothesis because there's a 100% chance that it is not stationary. Or that's not the proper definition of it, but you want your p-value to be low. Okay. So based on that, this time series definitely not stationary. So what are some methods that we can use to combat stationarity? Over in your labs, they go over a couple of different methods. For example, you can apply some sort of function on this time series. So I know that I think your Canvas curriculum will tell you one of the ways that you can do it is by taking the log of your data. So taking the log of this data, doing a dot plot, let's see what it looks like. It's kind of flattened it out a little bit. So here it ranged from 100 to 600. Although it kind of looks the same, the increase is not as, you can sort of see this is kind of exponential. The trend is kind of made a little bit less steep. So log transform is definitely one thing that you can do. But if you are to do a log transform, just remember or note down somewhere that you're doing a log transform to remove stationarity. Something else that you could do, you could also take the square root of your numbers. So I've seen that before. So if I do shampoo, will this work? To the power 0.5 dot plot. Okay, let's do this. There we go. Taking the square root has also made it a little flatter, but usually the most efficient way to remove stationarity is through a process called differencing. I'm going to talk about differencing. So differencing is one of the most popular ways to remove the data's dependence on time. Differencing is basically performed by subtracting the previous observation from the current observation. So basically, the difference at any one point is the observation subtracted by, or subtracting the observation right before it. So if you have a time series data set that goes like this, it's just a straight line up, it goes 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And we want to difference the lag by 1. And what this lag is, I'll tell you all in a little bit. What would this result be? Now, this is a really, really simple, well, it doesn't look simple, but it's basically a function that differences data for you. By the way, there's also a differencing method, which I'll show you all in a bit. But if we were to difference this and we set our interval to be 1, you can see that because each time step we're incrementing it by 1, the difference just becomes a flat line of 1. So if you had a lot of data, one difference of your entire time series is just going to look at the relative change in your data set. And that typically tends to remove the overall upward trend or downward trend or any sort of overall trend from your data. So as you can see here, if I had, if I have this line and I do, let's see, plt.plot, we do plt.plot, you'll see that this is a line that goes straight up. But now if I were to plot this, it is just a straight line across. So just by differencing it, we go from an upward trend to a detrended time series. Of course, this is a very simplistic example. Let's see what happens on our bigger data or on our shampoo data. So the difference, it's actually a pandas method .diff to difference. And when this is done, let me just run this real quick. You can see that the first observation becomes a null value. Every time you difference your data, you lose one data point because you can't really difference your first data point because it has nothing to difference from. So it's pretty normal to see a null value at the start of your difference data. But this is already here for you. If we were to plot this difference data, you can see that we have kind of pretty much removed this upward trend. So here we pretty much have a flatter time series. Any questions here? All right, so what we can do also, we can just do a Dickey-Fuller test on the difference data. If I run this over here, you can see now our p-value is well below 0.05. So therefore we can reject the null hypothesis and say that now this this data is stationary enough. So important to note that it just has to be stationary enough, a p-value lower than 0.05 to be used for time series modeling. Cool. Decupler of difference, all of this information as well. Okay, so about these number of lags used and how you can difference your data over and over again. Sometimes we have to difference the difference data to achieve stationary data. So fact of the matter is, sometimes if you have like a really strong trend or an exponential looking trend, you might have to difference your data more than once to achieve stationarity. And typically, the more you difference your data, the flatter your trend becomes. So one thing we can look at, we have our difference data here. I wonder if this will work. If I difference it one more time, it becomes even flatter. Actually, let me just put this somewhere else so that we can compare. Cool. So I guess it's not a super huge difference, but you can see that it's overall gotten a little flatter. I wonder if they'll let me do it twice. Cool. And over time, only the big shocks will remain. But overall, it should look flatter and flatter, less of a variance. I mean, these numbers are also bigger, but it needs to account for these shocks. Cool. Any questions about differencing at this point? Let me turn on the light real quick.
If we difference it more than once, is it going to affect the interpretability of the? Okay.
Good question. Yeah. You definitely will lose interpretability the more you difference your data. However, differencing specifically, let's just say you difference your data and you throw it into some model and it spits out values for you, but those values are different. That is not very useful for you. You can undifference data manually, but it's actually very, very difficult to do so. The neat thing is that for traditional time series models that we're going to talk about tomorrow, they will undifference it for you. So the amount of differencing that you include in a model will not directly impact the interpretability. If you were to do it by hand and build a model by hand and difference it a bunch of times, it will be very, very difficult to interpret. But we'll see stats models tomorrow. If you tell it that you're differencing your data, it'll undifference it for you automatically, so you don't have that interpretability problem.
Sweet, thank you.
You're welcome. And actually, that's a good point to bring up, because let's say you don't do something like differencing, but you find that something like log transforming was a lot simpler and a lot more efficient. If you were to log transform your data and you plug your log transform data into the model, no differencing included, your results will also be log transformed. So you just have to reverse log transform. But doing something that's something like reverse log transforming is a lot easier than reverse differencing, because how do you go from this back to this is a lot more difficult, because you sort of need to know the starting point and then be like, okay, if this value is 1, I need to know what the first value was, add 1, add 1, add 1 to bring it from this to this. So reverse differencing, much more complicated, but that is taken care for you within stats models. Other transformations for stationarity though, especially like things like straight up functions that you're doing, like square rooting or taking the log transform, you just have to reverse that on your own, but that's a lot easier to do. And we'll get into that more tomorrow. Cool. All right, so differencing removes trends, and it's a pretty efficient way to remove trends as well, and you might have to difference multiple times. Basically just difference until the Dickey-Fuller test makes it okay. Cool. So the number of times that you difference your data is the order of differencing. And again, this information is important when we build our model, because we'll see tomorrow that when you're building a model that includes difference data, you need to tell it how many orders of differencing to do. So therefore, when you do your EDA, take note how many differences your data needs to be stationary. That's something that you should remember, maybe make it into like a markdown header so that you remember. Cool. All right, so past differencing and the achievement of stationarity, the next thing we have to look at is autocorrelation. Autocorrelation is really interesting because it is kind of related to multicollinearity. And we'll get more into that tomorrow when we talk about the models. But if we remember from linear regression, we don't want multicollinearity. However, in time series, we can actually make use of multicollinearity in a way that benefits us. And it actually comes together really nicely. We'll see tomorrow. Basically, Time series exhibit two kinds of behaviors. Hold on. All right, okay, yeah. It's basically the concept that you can predict a value in a time series based on its past values. However, other times the past values can be misleading. Consider stock markets when there's a lot of randomness. Shocks can diminish quickly. This actually is not really relevant. But determining what past data we can use to predict future data can be very helpful, right? Like, for example, if I know that the prices of cars have been slowly increasing over the past few years, and I want to make a forecast of the price of cars 5 years from now, I'm going to make use of this past information to make my forecast and make my prediction. So autocorrelation is one way to help with that. And I do think it's quite intuitive. Well, part of it is intuitive. So let's take a look at autocorrelation. Autocorrelation, the definition is the correlation between one time series and the same time series shifted by a certain number of periods. So for example, if I have this shampoo data set and I plot the shampoo data set with the same data set but shifted one time step, how correlated is it? If I put it in a line graph like this, maybe it's clear, maybe it's not. If I plot it as a scatter, and this is with sales lag 2, actually, let me run this real quick. So I have shampoo sales, lag 1, lag 2. If I look at it like this is what my data looks like. I've kind of differenced it once, not different, shifted it once, shifted it twice over here. Now, if I take the correlation, we can see something really interesting. The time series itself has a 0.72 correlation with one shift and a 0.85 correlation with two shifts. So that means at any point, there is a pretty strong relationship with the point 2 periods ago, or even 1 period ago. There's a pretty strong correlation. If you remember from linear regression, I talked about the linearity assumption. This is kind of related to that. That something that's strongly correlated is likely to be a strong predictor for the target. So we can kind of use this, and there are cleaner ways to look at this. So here you can see this is the scatter plot of shampoo itself versus lag 2. You can see that, yeah, there is a fairly strong positive correlation. This is the one that has a 0.85 correlation. Of course, we only have 36 data points here, but that's not the point. Cool. So what are the built-in methods that we can use to explore autocorrelation? So there's actually two that you kind of have to look at hand in hand. So one is autocorrelation and one is partial autocorrelation. ACF, autocorrelation function, is the more intuitive one. PACF is when it becomes a little bit more abstract, but you usually look at these two together. So first, there's plot ACF. And how you interpret this graph, and you should make this graph for your time series as EDA, is if you look over here, these, I guess, lollipop looking things, these basically represent the correlation between the time series data and the data itself shifted by K data points. So for example, this is what we saw before, right? The correlation with one time shift is about like 0.7, and with two time shifts is closer to 0.75. And over here, we can see that as we get further and further away, the autocorrelation starts to decrease, which makes sense because values that happen right after one another are usually closer together. So what we're seeing is with more time shifts, we have gradually decreasing correlation with the time series itself. Questions about how we understand this graph? Or is anyone like not understanding what I'm saying about this graph? Because this graph is kind of important. Cool. So this blue cloudy area is your confidence interval. And you kind of want to see what points are outside of this confidence interval. So here, I'll actually take note to say that, all right, the first two lags have significant correlation. Note this for future model building. So when I see this, I should make a note under this graph and say, all right, based on the ACF, there is strong autocorrelation or relatively strong autocorrelation for the first two lags. So what is PACF? When this is this next thing that we're going to talk about. So sometimes autocorrelation propagates down to other lags. So the influence of a strong autocorrelation will cause additional lags to be highly autocorrelated. To discover true relationship between lags, we can use PACF, and that's partial autocorrelation. Now, that was kind of abstract, but PACF aims to find out the true correlation without the effect of intermediate lags. So if you just imagine, we have a time series that looks like, I'm going to just draw a janky time series over here. Let's just say we have a time series. Let me change the color. Let's say we have a time series that looks like this. We have a time series that looks like that, and we shift it by 1. Let me choose a different color. We shift this over by 1. We can guess that this first time lag will be pretty correlated, right? And as we keep shifting this down the line, we're going to get less and less correlated. So this will be one that's way down the line. And at some point, you might even get like opposite correlation. These lines will not be very correlated, but it'll become less correlated because it's moving further and further from the original time series. So because of that, we can say that sometimes a lag that is over, actually, let me make this a little cleaner. A lag that is over here has a correlation value of, for example, it has a correlation value of 0.4. How much of this 0.4 correlation is because these other lags were already pretty correlated? So that's why we need to look at partial autocorrelation. How much is the correlation of this orange line without the effect of the correlation of the blue line? Questions about that? I know that's super abstract.
It's basically comparing it to the origin and not the previous, correct?
Yeah. Yeah.
Just want to make sure I understood that.
Yeah, that's like comparing it to the origin without the effect of the previous ones. Although like these autocorrelations, you're actually comparing this with this to get this value, if that makes sense. So it's also kind of comparing it to the origin, but for PACF, which is the one later, we're comparing it to the origin without the effect of anything that happened between it. So you're trying to separate the effect of lags number 1, 2, 3, 4 to find the correlation of 5 just by itself. Anywho, PACF, you kind of interpret that in a very, very similar way. So PACF usually looks a little bit more erratic, although not always. But PACF, you can see that the correlation dips down much quicker because it is saying that, all right, at lag 3, a lot of this autocorrelation, you see how this is kind of right at the boundary, probably was due to the high autocorrelation in lags 1 and 2. Therefore, here it quickly dips down. In this graph here, we can see that lags 1 and 2 are still high, even in the partial autocorrelation plot. And that's something that you want to take note of as well. So for both ACF and PACF, you should take note how many lags or how many time shifts are significantly correlated. And you will use that for your model building. And here, yeah, it's just different plotting function, but you use it in exactly the same way. Cool. So things to note for, oh, question. I saw Sam came off mute.
Does this also help us decide how many like difference bubbles to do in any way or no?
So that's a good question. And I was going to talk about that tomorrow.
No, you're fine. You're fine. No, I'll wait. Sorry. I just want to make sure.
Actually, this is useful, especially as you're prepping for getting to modeling. This doesn't necessarily tell you how to difference your data, but that's a really good point that you bring up differencing, because you should do this independent of your differencing. Actually, if you find out that your data needs to be different, so let's say you find out that for stationarity, your data needs to be different 3 times. What you should do for your ACF and PACF graphs is actually run them on 3 times difference data, because the effect of looking at correlation and differencing is independent when you're building your model. And that will make more sense when I talk about models tomorrow. It's just how it's structured. But yeah, if your data needs differencing to be stationary, you run your ACF and PACF graphs on your difference data. Cool. Also, if you see that you have seasonality in your data, I know this is kind of overcomplicating things. Actually, in the project data set, you don't have to worry about seasonality, and seasonality is also actually part of the appendix, so it's not necessary, but very good to know. If you see seasonality in your data, you should actually run your model on, or you should actually do your ACF and PACF on the residual component, or on any component that isn't the seasonal component. But we're kind of complicating things now, but that's what you should be doing. But we don't have to worry about seasonality for now. Cool. So given this shampoo data set, what have we taken note of? So first, ACF has 2 significant lags and decreases gradually. PACF has 2 significant lags and drops off, and also that our data needs 1 level of differencing. Actually, what I should have done is reran this on difference data. Maybe I should do that. Let's see if this will throw me an error. Okay. Never mind, let's ignore that for now, because I think, yeah, I should have done this on the difference data, but we're going to talk about more of that tomorrow. Today, we're just talking about the different EDA things to do. Cool. So now that we know how to analyze patterns in our time series, we can proceed with creating models to create forecasts. Now with these 3 numbers, number of autocorrelated lags, number of partially autocorrelated lags, as well as the number of differencing, number of the order of differencing that needs to be done, you can pretty much start building your time series models. And we'll talk more about that tomorrow. But cool. Any questions? I'm going to send out this resource because I do think it's very cool. I'll send it out to the Slack channel right after this.
I have a question. So this kind of EDA is done on each variable. So like if you have the 200 zip codes, it needs to be done separately for each of the 200.
Yep, that's right. And that's why I feel like it is very complicated to do that project. There are ways to, there are definitely ways that you can functionalize this process such that it's doing it much quicker. And tomorrow I'm going to talk about a way where if you don't care about EDA and you have a lot of time series to build, there's a way to actually automate the entire building, the entire time series process, but you don't learn anything out of automating the whole thing. So I'll share that tomorrow.
Okay. And then like, I guess when you model, you want to look at each one regardless, right? Like very specific or separately. Okay.
Yeah, you should, unless like, you're trying to churn out, I would say in like the project and the way that it is framed, when you have to build time series models for 200 of them, you should not be doing EDA on 200 different time series. However, you should find a way to like aggregate the information and quickly use the information, if that makes sense. Maybe you do the EDA for a couple of them and then repeat the process on the rest. But yeah, I'll talk more about like how to perform this in context of the provided project specifically tomorrow.
Okay. Because I was thinking, I'm like, maybe for 1 zip code, you might need like 2 differencing versus like 3 on another one and stuff.
Yeah.
And then I guess recording each one might be a nightmare.
Yeah, you're absolutely right. It is 100% very, very time consuming, and also very like, because this is us interpreting the graphs, and I feel like it doesn't make sense for us to interpret 200 zip codes. The project, by the way, is also not asking you to do that. So I'll talk about how you can do that in a more automated way tomorrow.
That's it. Thank you.
You're welcome.
I had a couple of questions. So just based on what you were saying just now, will we just create a function that would automate that? Would that
pretty
be
much?
Okay.
Yeah.
And,
I have had. Oh, go ahead.
No, I'm sorry.
Right. I was just gonna say that I have students doing their capstone project, and I have people who are kind of like pick stocks in the stock market. And as an example, you can just completely automate the process. For example, like save the number of autocorrelated lags, save the number of differencing that you need, save it in some form, and then you can just create models specific to each stock.
Okay.
Yeah, and you do that through functions.
And for differencing, maybe I'm reading it wrong, but what are we altering when we're doing the differencing? Like
Differencing is mainly for detrending. So it turned our data from this to flatline. We don't want that overall trend in our data.
Right,
That answer
but
your question?
if we're doing another, if we're doing it again, like if we're doing it, what do we?
What are we
all-
achieving by if we keep doing differencing over and over?
Well, I just think about like max depth, not to like confuse
okay.
people, like if you change max depth for your decision tree, it's changing the model. What do you change with points? I don't know if that makes sense.
That makes sense. That makes sense. For differencing specifically, it changes the data that goes into your model. So it is for these sets of models that we're going to talk about tomorrow, it works better on data that is stationary because that is one of its assumptions. Differencing is just it's actually a pre-processing step. But the pre-processing step and why we take note of the amount of differencing for our model is because the models for stats models, it does the pre-processing for you. So in a world where stats models doesn't exist, you would actually do this as a form of like your data prep or pre-modeling data cleaning.
Okay. All right.
Yeah.
Thank you.
I know that's really confusing, but hopefully tomorrow will like illuminate a little more.
All right. Thank you.
You're welcome. Anything else? I know we have a lot of loose ends today, which tomorrow will help with. I hope, I'm sure. Cool. Actually, since we're here and we have a little bit of time, let's just say that for this, we figured out we have 2 significant lags for ACF, 2 significant lags for PACF, and 1 order of differencing. I'll show you all real quick what that looks like. This is a notebook I'm going to go over tomorrow. And I'll explain all of this stuff tomorrow as well. But in our model, so earlier we said two significant lags, 2 significant PACF lags, and then 1 order of differencing. Those are the numbers that you literally plug in over here. So this is a different model, but with that data, I would do 2, 1, 2, and I'll talk about why that is tomorrow. But this is basically number of significant ACF, number of significant PACF, and number of lags. So we'll get more into this tomorrow, but that's why those numbers are important to just write down on your notebook and analysis. Cool. All right. Anything else? And let me just clear this for tomorrow, so no spoilers. All right. If there's nothing else, I will see you all tomorrow. By the way, I'm out of office on Thursday. I'll remind you all tomorrow again. But none of you meet with me on Thursdays anyway, so that's cool. All right, just in case you're trying to reach me on Thursday, I won't be around. I'm finally moving all the big stuff over. So yeah, I'll be back on Friday though. Okay, I will see you all tomorrow. You have a good rest of your night, everybody. And we'll talk some models tomorrow. Bye, everyone.
All right.
Good night. Thank you.
Not everybody.